Hi everyone, my name is Neha and this is the seventh lecture on Introduction to Automation. In this lecture, we're going to learn about load sensors. Load sensors, they are defined as a transducer that converts an input mechanical force into an electrical output signal. They can be hydraulic, pneumatic, or most commonly based on strain gauges. When a load sensor is connected to an appropriate electronics, then they can return a signal which is proportional to the mechanical force applied to the system. Here, on the right side, you see some of the load sensors which are used, and you can see how different they look. These load sensors, they can be used for a variety of applications. For example, in kitchen and bathroom scales. They can also be used in self-service checkout. They are used in weighing luggage at the airport, and they are used in pallet weighing. And there are many more examples where load sensors can be used. Now we are going to see the Hooke's law, which is used in the load sensor, and it is given by this formula. F is equals to Kx, where K is the spring constant of the material, F is the applied force, and X is the extension or compression as result of the force. And we can see this example. If a mechanical part has a spring constant of 1000 lb per inches and it is compressed at 0.5 inches under the load, then the load must be of 500 lb. So this you can obtain by putting these value into the equation. Then you would be able to get this result. Now let's see different types of load sensor. So here is the list of all different types of load sensors, and I'll just quickly go one by one. So we have here bounded wire strain gauge, hydraulic load cell, pneumatic load cell, piezoelectric load cell, semiconductor force sensors, low force sensors, vibrating wire load sensors, capacitive type load sensors, beam load sensors, bending beam load sensors, platform and single point load cells, canister load cells, low profile load cells. So all these are your load sensors, and next we are going to see bonded wire strain gauges. So bonded wire strain gauges, they can be used to measure wide range of forces from 10 lb to many tons. And they use the special type of material which is called a strain gauge material, and the material construction of the wire, they directly affects the sensitivity of the strain gauge. Now let's see some example materials which are used in construction of the strain gauge. So we have first constant and alloy wire, and these are used for applications where you encounter plastic deformation, and they cannot be used for any extreme operating conditions such as high temperature. Next we have isoelectric alloy wire, and these are used if high signal noise ratio is required, and their goal is to measure the dynamic strains. And then third we have Karma alloy wire. They are used for application which involve low temperature environment as low as -269 degrees Celsius, or temperatures that may vary during the measurements. Next we have platinum alloy wires, and these platinum alloy wires, they are used for measurements where you want to work on a very high temperature. So they can be used for temperature greater than 230 degrees centigrade. Now let's see the circuit. In this circuit we see this active gauge. From this active gauge the main force is applied, and then we see this compensation gauge. This compensation gauge is used in order to help in cancellation of the variation due to temperature. Now let's see the working. If the object is put under tension on the strain gauge, then it will stretch and elongate the wires, and the wires will not only get slightly longer, but they also become thinner, and that change is basically taken over here and through these voltage junction V1 and V2 we can get the output voltage, and that output voltage will be obtained from this operational amplifier. Now here to this bridge circuit, the supply is given through this Vs. This is the supply voltage, and any change in the force when it is applied on these gauges, that change will disbalance the circuit, and that change can be obtained over here at the output. Now the change in resistance can be obtained by this equation, where R is the resistance of the length of the wire and rho is the resistivity, and it is a constant. It depends upon the type of material you are using. L is the length of the wire and A is the cross-sectional area of the wire. Now let's see the bridge circuit analysis for bonded wire strain gauge. So here you see this circuit where this RG is the active gauge and RD is the compensation gauge, and R1 and R2 are the resistances, Vs is the supply, V1 and V2 are the junction voltages, and V is the total output voltage. So at these two junctions, if we use the voltage divider formula, then we will get these two results, where V1 is equals to Vs. Vs is the total voltage for this junction, and the resistance we are measuring across is this Rg. So V1 is equals to Vs Rg upon R1 plus Rg, and we are measuring the voltage V2 across this Rd. So it will be equal to Vs Rg by R2 plus Rd. Now the voltage across the bridge can be expressed as V1 minus V2. So here these two voltages are going, and so it will give a V1 minus V2, which is your delta V. And if you put these two values into this equation, then you will get this formula. Now let's assume that all the resistance in your bridge circuit, which you saw here, they all are R. So for example Rg is R, R1 is R, R2 is R, and Rd is R, and all these resistances their values are same. And what will happen if a force is applied, then there will be a change in resistance of this strain gauge. So this new resistance will be, let's say it will be R plus delta R, where delta R is the change. And if you put that value R plus delta R in place of Rg, while rest of the resistances remain same, which is R, and you put that value into this equation, what I mean is in place of Rg you write R plus delta R, and in place of R2 you will just write R, and Rd will be just R, and R1 it will be just R, and this will be R plus delta R, and this will be R plus R. So if you put this value, then you will get this equation, and once you get this equation, then you see at the denominator that your 4R is much higher compared to 2 delta R, because delta R represents the change and it's going to be small, and this value is going to be higher compared to this. So we are going to make the approximation, and we are going to ignore this, and we will just put delta V is equals to Vs delta R by 4R. So once you have that equation, you can find the value of delta R, which will be approximately equal to 4R delta V upon Vs. We have this approximation sign because of this, because this is definitely going to affect, but the effect is very small, and that's why we have taken this quantity here. So this will be our final equation, and this is the approximate equation, where delta R is the change in the strain gauge resistance, and R is the nominal value of all bridge resistors, and delta V is the voltage detected across the bridge, and Vs is the supply voltage or the source voltage applied to the bridge. Now these two important topics we need to learn in the bonded wire strain gauge. The first is the gauge factor, which is also called as strain factor, and it is basically the ratio of relative change in electrical resistance to the mechanical strain. So this is the gauge factor, and this is the strain which I'm talking about. And let's see what are these what is all these parameters are. So E is the elongation of the object per unit length, delta R by L, and it is also called strain. And then we have the R is the strain gauge resistance, delta R is the change in the strain gauge resistance when the force is applied, and then GF is the gauge factor. It is a constant supplied by the manufacturer. And then we have the Young's modulus, and Young's modulus is a measure of how stiff a material is, and it could be thought of as a kind of spring constant, and it is in equation form it is equal to the rho by E, where rho is the stress and E is the strain. So Young's modulus is basically the ratio of stress upon strain. Now let's see one problem based on a strain gauge sensor. So this problem says a strain gauge and bridge circuit are used to measure the tension force in a steel bar. The steel bar has a cross-sectional area of 2 inch square. The strain gauge has a nominal resistance of 120 ohm and a gauge factor of 2. The bridge is supplied with a 10 volts. When the bar is unloaded, the bridge is balanced, so the output is going to be 0 volts. Then force is applied to the bar and the bridge voltage goes to this, which is 0.0005 volts. Now you have to find the force on the bar. So to calculate the force on the bar, we will use the formula which we have seen previously. And here, if you notice that we are using the steel bar, so for steel bar we'll be using this value. So let's see. First you are going to calculate the change in the resistance. So R already given in our problem, which is 120 ohm. Delta V is the change which has happened, and it is this value, and Vs is the supply voltage which is given in your problem. The bridge is supplied with the 10 volts. So we have this, so this is the change in the resistance. Now next, which we are going to calculate is the strain, and this strain can be calculated by this formula, delta R by R upon GF. Delta R we already know, we have found it, and R is 120, and gauge factor for this is 2. Let's see if it is given in the problem. The steel bar has a cross-sectional area of this, and it has a gauge factor of 2. So yes, this gauge factor is already given in our problem. So we'll put that value into the equation, and we will get this much answer. Now next, which we have to calculate is the stress. So the stress can be calculated by multiplying the Young's modulus with the strain. So the Young's modulus for the steel we have seen in the table here. This is the Young's modulus given for the steel is 30 cross 10 raised to power 6. So we will put that value here and then multiply with the strain, and then we will get this value. Now this value which you see here is just for 1 square inch, and we have to calculate it for cross-sectional area of 2 square inch. So what we are going to do, we are going to multiply 2 with this, and then we will get the final result. So let's read here. This result tells us that the tension force on the steel bar is 3000 lb per square inch, and because this bar has a cross-sectional area of 2 square inch, the total tension force in the bar is going to be 6000 lb. So this is the force which we are going to have on the bar, and this is also called your stress. So this is the end of the lecture. Thank you so much for watching.